There's a topic we really often just touch upon, but never really go into depth with it. It's like a bi character. It's Robin to the Batman that is not really that important, but really maybe Robin is the one that saves the day. And the topic is measurement system analysis.
Yeah, measurement system analysis, kind of a boring name, sounds boring, doesn't really get you excited. And ultimately, all you're going to find out is how well can we measure the thing that we need to measure. And that's like, it's really important, but it's not the most exciting part of the scientific discovery process.
Now, I feel like going to the upper management, let's say I have two projects. One is the DOE to improve yield, and the other one is a DOE to figure out whether we can measure yield.
Right.
Yeah, they'll go for the one to improve yield, right?
Yeah.
You told me an anecdote about why people shouldn't skip this part. Can you rephrase that for me?
Yeah, absolutely. So there was a group of scientists trying to improve a process. They were trying to understand factors affecting a chemical reaction. You can either get 0% chemical conversion up to 100% chemical conversion. And they were trying to understand the factors affecting this. We designed an experiment. It wasn't a huge experiment, but still a significant investment of time, a week or 2 weeks worth of work in the lab, doing these, changing the factors, seeing how it, trying to understand how it affected the chemical conversion. A couple of weeks later, we got the results in, and they'd done 3 center point runs in this experiment. So 3 runs with exactly the same factor settings, everything set at the center point of the factor ranges. And the results for those 3 repeated runs came in at 20%, 50%, and 80%. And that was basically the whole span. All the other runs were within that range. So we had no hope of learning anything about what was affecting this conversion because we just couldn't consistently measure the same result when we kept everything the same.
How would you think it would have looked if you had done those 3 center points as experiment 1, 2, and 3?
In retrospect, I think we should have done that. So this is one of R.A. Fisher's original principles of designed experiments, is that you randomize your experiments. There are good reasons for that. But in this case, it would have been great if we'd just done those 3 center points first, and we would have not wasted time doing the other 8 or 16 runs.
Point 1 for this video. If you can't answer the question, what's the measurement noise, you should look into it before trying to improve anything. I have 2 real-life examples that we'll go through. And the first one is kind of funny. I'm very conscious about how much meat we eat in our family. And I'm a person that measures everything. But having 3 small children, it's really difficult to remove it from the table because it's easy. I know how to work with it. And the few times I've been making meatballs for my family, I've noticed I'm not getting my full worth in that pack. And I'm like, and it's been repetitive. I'm like, So I came to wonder, can I prove statistically that I'm being cheated?
Right. Okay.
So right now I have a sample of 1, and it was at 492 grams with the weird sheet of paper. There's a sheet of paper in the bottom that I weighed with it, and I actually also tried to get out all the juice and stuff. 492. I have a really good weight. It doesn't have decimal points. So we already now know the uncertainty is at least a half gram.
Right. Yeah.
Because it's going to round to full numbers. So there's probably other things in the uncertainty that we could add. But let's just go with the 0.5 because it's a very accurate weight. So I think it's more precise than the rounding. So we have the difference to detect is the difference between what I got and what they're saying I'm getting, 492 to 500, and the noise is 0.5. So let's try and do a sample size calculation. So I'll open up Jump. Okay, so am I being cheated? And why does this matter to what we're talking about? Well, it's because ultimately, if I want to prove that I'm being cheated, I need to know the noise of my measurement, as we discussed, and we've already defined the difference to detect. So I know in Jump there's a sample size explorer. Let's do for 1 sample mean, right? So I'm going to have 1 sample of portions that I buy. And it's not 2 dependent samples. So I have a strict point of 500 grams and I have 1 mean that's going to vary. So I want to be certain that I'm right. So I want to have maybe a low alpha and a really high power. So that's going to boost up my sample size. But I think since the difference to detect and noise is so massive, I think actually that'll work out okay.
Yeah, so I think it's worth, first of all, just saying what power analysis does.
So I think you're right. Before we answer the question that I came with, let's just walk through this and how we should understand what we're looking at. So let's say this is our upper bound of 500 grams, right? And I want to prove that's we're not there. So
Yeah.
if I take a sample of one, which I've done right now, I will have a data point here. And that made me curious, saying, I don't think that that's true. I think I'm being cheated, but I need more data to prove that. So now the question is, what is the sample size, Christian? And I will then ask, well, what's the noise? And in this case, the noise is equal to the uncertainty of my weight. Let's say I'm really right and the points are really centered around the same point. We will not just get a mean, because no one is really interested in the mean point. So this is going to be the mean. This is X bar. What I'm really interested in is showing that the uncertainty is far away from what they're trying to say it is. So once that uncertainty is fully outside the target, but then I've proven it, right? So that's when p-values get below 0.5 is when the upper confidence band is fully outside the detection limit. So let's say my data is more noisy. I would probably have gotten something like this. I'm not able to prove because it's more noisy.
Significant chance there that the true mean of the sample sizes, the true weight of your meatball packets actually is above 500.
So the last thing to say is that where this chart will never end. So you need to make a cutoff that you're happy with.
Yeah.
So that's if the cutoff was 0.10, we could choose an alpha of 10, and that gives us here. But then we're okay again, right? Then our upper confidence band is below the target. But if it's 0.5, it's going and it'll be there. So this is an alpha 0.10. This is an alpha of 0.5. And one I will be able, and the other I will not. The first thing is this one-sided or two-sided? It's one-sided because I'm okay with getting more. Where is that cutoff? Like, how certain do you want to be that your range of noise includes the actual true mean? And if you want to be like the standard would be 5. If we set this to 10 in this example, we will be able to prove it. And in my other example, this will not be able to prove it. Then the question is, let's just keep it at 5. And given we have a noise that is twice the size or twice the size of what we're trying to detect, if I run this setup 100 times, 61 of those, I would be able to prove that my the confidence band would be smaller than the upper limit of 500.
Yeah. So that's running 100 times, running a sample size of 30. 60 out of those 100 times, there's going to be a significant difference between the confidence interval around your mean and the target value of 500.
So you could ask yourself, are you happy with that? Would that be okay? Given that I'm actually going to buy something, I would like to be more certain than that. But luckily, my noise and difference to detect is really different than we're seeing here. What we discussed is that the noise of my measurement is 0.5. Let's just keep the difference to detect. I will actually say that if your noise is equal to your difference, let's do it to 80. We could just do 8. If you want to be more certain, we could do 11. So this kind of shows how dependent your sample size is of your noise.
Yeah.
And what's the noise? It's the measurement system and the way we make measurements, right? If I were to actually go and buy something, the setup for me, I'll do really high, low alpha. But my difference to detect is 8. So if I just want a power of 95, I just need to go and do a sample as 3. But that's saying if I'm right. If I'm actually right that the difference is 8, I just need to go and buy 3. If that was actually just 5, 3 would still be fine. Let's do 2. Wow. Yeah. Now it's lower. So if the difference to detect is just 2, like just a quarter of what I think it is, I would need to go and buy, if I want 90, 195. I would just need 5. That is what I'm going to do. But we will return on this on another video because I do think they're cheating me. So I just need to go and buy 4. If the difference to detect is just 2 grams and I have an uncertainty of 0.5 in my measurement system, there's 96% chance that I will detect that. Are you seeing any
Yep.
flaws in my approach?
No, I think it's right. The difference to detect is a strange thing. Again, it's not how we traditionally frame things as a scientist or an engineer. We're not often thinking what size of difference are we looking for. Um, so this is all about it's an estimate of what the signal is. What size of signal do we need to be able to detect? If we don't care, like in your example, if you don't care if the difference between what it says in the packet and what you actually get is 1 gram, that's not an important signal to you. What is an important signal to you? Yeah, it's up to you to decide. There's
Yeah.
no nothing. Nobody else can tell you what's important for you. Is that 2 grams? Is it
Yeah.
5 grams? Is it 10 grams?
In other words, if you're changing from one system to the other, and the other system is really expensive, how much of an improvement would you like to see? And that would then be your difference to detect. Let's try and phrase that question that we don't actually ask ourselves as scientists. So people are going to have it written out and posted on a wall. So let's do our best. So I've made a suggestion. So let's see here. Given an X difference to detect with a noise of Y, the power will show us the likelihood of proving that we are C confident that the true value is different than the target. That sounds really weird. And that's probably not how it's said in the textbook. That's my take.
No, I think it's good. A statistician would almost certainly pick you up on it and have some criticism of it. But I think to the layperson, it makes a lot of sense, or it makes as much sense as it can. It's not a simple concept, power.
Yeah. Let's try and convert this sentence to my problem then. I want to prove given, and let's just say 2 gram. Given I want to find 5. If it's 5 grams difference, I will send them a mail and we'll see what they say. Given a 5 gram difference to detect with a noise of
0.5.
The power will show us the likelihood of proving that we are 99% confident that the true value is different than the target. How would you phrase just my example?
Well, there is a 96% probability of detecting a difference of 2 grams with a sample size of 4, given a noise of 0.5 at an alpha equals 0.01 significance level.
We kind of derailed from the measurement system analysis that we talked about in the beginning, but I do believe this is super still on point because it shows people the first question I will ask you is, when will you deem this to be actually important to you? And most often they say, well, I don't know. They say, you need to know.
Once you've done that, then what is the noise? How do you know that? Are you really sure about that? Is that just a guess? Is that just what you think it should be, what you'd like it to be? Or do you really have data that tells us what the noise really is?
All right. Well, thank you. Thank you, Philip. Thank you for joining me. I'm looking forward to seeing how people will react to this. This is a question I get a lot. Really, if they watch this video, they should be able to answer that themselves.